Okay, so in this video, what we're going to be looking at here is how to use this simulation and what is this simulation based on. So before I actually get to what these different probes are and how to calculate the absolute age, let's just go back and look at this measurement. Now, there are two main kinds of probes on here that we're going to be using. One's carbon-14, and the other one is uranium-238. These are both radioactive isotopes, which means they go through radioactive decay until they become a more stable isotope. And carbon-14 is something that you're going to use on things that are or were once alive. Now, when things are alive, they are breathing in the atmosphere. They are breathing in this radioactive carbon-14 that's found naturally in the atmosphere. All right? So, for example, if I plant a tree, it is always absorbing this carbon-14. But if I were to kill it, all right, or eventually it dies, it's no longer respirating. And that carbon-14 that has been taking in is now going to start to decay, right? Because the plant is not actually replacing that carbon-14. So it's decaying. We can see that here, all right, that we had 100% of carbon-14, but as soon as it died, that carbon-14 began to decrease in amount because it's going through radioactive decay. And when it gets to this one half-life, we know what half-life is, when half the amount decays. Now, we went again another half-life, we should get down to half of what remained, that 50%, half of that's going to go away. It's going to get down to 25% and so on. All right. So that's for carbon-14. All right. It had a half-life of roughly 5,730 years. All right. Every 5,730 years, half of whatever carbon-14 it had before is going to decay. However, all right, if we were to change this up, all right, and instead look at a volcano erupting, that magma and lava comes spewing out, and it will eventually cool. All right, well, we can't use carbon-14 to date this because there is no carbon-14 in it. However, uranium-238 is a naturally occurring substance that is found in the soil and in a lot of igneous rocks. That's why we don't actually date sedimentary rocks directly. That is actually quite hard to do. We can date igneous rocks very well because we can use uranium-238 or other substances that are radioactive. But again, the half-life of uranium-238 is 4.5 billion years. So if we could watch the amount of uranium-238 in a rock go through radioactive decay for 4.5 billion years, we would see that roughly every 4.5 billion years, half of it goes away. Right? So any of the substances on the dating game tab that are rock, right, you're going to use uranium-238. Anything that was once alive, you're going to need to use carbon-14. So let's go ahead and jump into this. So we're going to start off with just something up top here. Let's say, actually, let's go with this bone right here. Right. If you move the sensor over the bone, right, we're going to be using the carbon-14 probe because it was once alive. Now, in the last activity you guys did, or worksheet, we did a very simple form of radiometric dating. If we know how many half-lives it's been through exactly, we can figure out how old it is by just taking the number of half-lives times the length of a half-life. However, the chances of it being an exact number of half-lives is pretty slim. And most of the time, it's somewhere in between, half-lives. For example, if this had been through one half-life, this would be gone down to 50%, but it's actually not. It's only 83.9% carbon-14. So it's only lost 16.1% of the carbon-14 that it originally had. So the math is a little more complicated, but what we can do is just allow this simulation that shows the radioactive decay of that carbon-14 to do the math for us. So what you're going to do is you're going to use the appropriate probe type and this percentage, and then you're going to move this slider over to match up this percentage or get it as close as you can. So 83.9, and the closest I can get is, well, either one of these, 83.7 or 84.1. So either one of those is going to be fine. And then all you're going to do is take the age and type it in here. All right. Now, since it couldn't get to exactly 83.9, there is a range of acceptable answers here. And to check your estimate, it'll give you this nice little sign. If, for example, you did something wrong, saying this is 1,000,000, it's going to give you the no. All right, and you want the right answer, obviously. But if I try to use that carbon-14 again on something that was not once living, all right, it's going to say there is no carbon-14 in that because this wasn't living. Or if something was living and it's really, really, really old, all right, there is a chance that it's so old that all the carbon-14 has gone through radioactive decay. And you're going to have to use either the uranium, say on this rock, we're going to use the uranium, or on some of these, you're going to have to use just a custom. Okay. So now if we have a custom, what you're going to actually have to do is choose an appropriate half-life. Right? If you choose too small of a half-life, all of the radioactive material of this custom sample might go away. All right? If you pick too long of one, it may be not enough time for it to have decayed.